June 30, 1908. In the far reaches of central Siberia, where maps faded into blankness and rumor, morning came slowly over the taiga. The sun, low and pale, eased itself above an unbroken horizon of larch and pine, its first rays sifting through veils of mist that clung to the marshes and low river valleys. The air was cool, but already hinting at the brief summer's warmth, smelling of resin, damp soil, and smoke from distant campfires where reindeer herders and trappers were stirring to life. To the few people scattered across this immensity, the Evenki herders in their tent camps, Russian settlers in rough wooden huts, hunters moving silently through the trees, it was a morning like any other. Dogs padded between shelters, noses twitching at the scent of boiled tea and fresh-cut wood. A herder stepped from his tent, squinting into the pale light, listening to the soft jangle of reindeer bells and the distant calls of the forest's birds. Somewhere a child chased a stray calf through the dew-soaked grass, while an old woman bent over a small fire, coaxing it back to life with careful breaths. The taiga spread in every direction, a green ocean of needles and trunk broken only by winding rivers and bogs that gleamed like scattered mirrors. It was a landscape of extremes, winters so cold the air itself seemed to crack, summers so brief that life burst forth in frantic abundance before the long freeze returned. Beneath the thin skin of soil, the ground lay locked in permafrost, hard as stone, anchoring the roots of larch and pine while limiting almost everything else that tried to grow. To human eyes, it was a realm that seemed timeless and indifferent, a place where seasons, not hours, marked the passing of time. By human standards, almost nothing happened here. There were no cities, no railroads, no dense webs of telegraph lines, only the occasional trading post or frontier village days apart by horse or sled. Messages moved slowly, carried by word of mouth and the rare official courier. News from St. Petersburg or Moscow, if it came at all, arrived as rumor months late and half-remembered. In this stillness, the cosmos itself seemed very far away, a distant canopy of stars that mattered only for navigation and myth. Yet on that particular morning, something was coming. Far above the blue vault that the herders and settlers knew so well, an object had crossed Earth's path in space. It was much too small to notice in the emptiness between planets, perhaps only a few dozen meters across by modern estimates, yet large enough to carry the energy of many millions of tons of TNT. For untold ages, it had wandered the solar system, a fragment of larger bodies broken and scattered in ancient collisions, circling the sun in a silent, invisible orbit. As dawn brightened over the Podkamonaya Tunguska River basin, this tiny wanderer struck the upper layers of Earth's atmosphere at tremendous speed, tens of kilometers per second. The friction of the air, suddenly no longer empty but thick and resisting, began to eat at it, compressing the air in front of it into a shock-heated sheath of incandescent gas. To anyone looking up at the right moment, it would have first appeared as a distant spark, then a streak, then a roaring pillar of fire tearing across the sky. For those on the ground, the first hints were subtle, a faint tremor in the air, a distant rumble like far-off thunder. A trapper paused on a game trail, one hand on the rough bark of a larch, brow furrowing as the quiet morning soundscape changed. A dog stopped mid-bark, ears pricking uneasily toward the sky. Over a small village, a farmer glanced upward, puzzled by a growing brightness in the corner of his eye. Then the sky changed. The deep, ordinary Siberian blue, so familiar that no one ever thought to question it, began to pale and then flare, as if a second sun were pushing through from behind. A column of incandescent light stretched across the heavens, so bright that it cast sharp shadows on the ground and made people shield their eyes with their hands. Witnesses would later describe a bluish-white body, impossible to look at directly, moving across the sky and trailing a luminous wake. One man, eating his breakfast outside his home dozens of kilometers from the epicenter, would recall how he saw the sky seem to split apart, the northern half igniting in a sheet of blinding flame. The sound lagged behind the light, but when it came, it arrived in stages, first a rising roar like a locomotive rushing overhead, then a succession of monstrous cracks and booms that seemed to come from everywhere at once. In camp after camp, people staggered to their feet, shouting to one another, unsure whether the danger lay on the ground or in the sky. Some stared upward, transfixed, while others dropped to their knees or fled toward the tree line in blind instinct. As the object plunged deeper into the atmosphere, the stresses on its body mounted beyond endurance. The surrounding air, compressed and heated to thousands of degrees, battered it with invisible hammers of pressure and heat. At an altitude of several kilometers above the forest, modern studies suggest roughly 5 to 10 kilometers, the body catastrophically failed. In a fraction of a second, it broke apart and exploded, converting its enormous kinetic energy into a vast, expanding fireball and a brutal shockwave that raced outward in all directions. To those directly beneath it, the world ended. A blinding flash turned the sky white, bright enough that people later described it as more intense than the midday sun. Faces and hands burned as if held too close to a furnace. Breath caught in throats as the air seemed to turn solid with heat and light. Then the shockwave struck. The blast wave swept across the taiga at supersonic speed, flattening trees as if they were blades of grass before a scythe. Reindeer were hurled into the air, storage sheds and tents collapsed or were flung aside like toys. People nearest the blast were picked up and thrown, some losing consciousness before they even hit the ground. In a few cases, according to later reconstructions of eyewitness reports, individuals died when they were slammed into trees or struck by falling debris. A herder standing on a low rise, watching the mysterious fireball, felt the ground shudder beneath his feet. An instant later, an invisible fist struck him in the chest, sending him tumbling backward through the air. He landed hard, the air blasted from his lungs, his ears ringing so violently that the world seemed to dissolve into a high, continuous whine. When he tried to stand, the forest around him was no longer recognizable. Trees uprooted and laid flat, branches snapped, needles stripped from limbs and scattered like green snow. 30 kilometers from the epicenter, the devastation was still astonishing. Entire lines of trees fell in the same direction, as though pressed down by a giant unseen hand. Roofs collapsed inward, walls buckled, and fires started where the intense heat had ignited dry wood or brush. People crawled from the wreckage of huts and storage shelters, dazed, some burned, some bleeding, all of them terrified and bewildered. Farther out, the event still felt like an assault. Around 60 kilometers away, people were thrown to the ground by the force of the shockwave, and windows shattered in small settlements, sending shards of glass flying across floors and into faces and hands. The explosion's roar arrived as a rolling, complex sound, a single colossal detonation followed by a series of echoes and secondary booms that many likened to artillery or distant cannon fire. Some villagers, living in an age of rising geopolitical tensions, were convinced they were under attack. At distances of around 170 to 200 kilometers, people still saw a fireball in the morning sky, a brilliant sphere or elongated shape, far larger than the sun, glowing with an intensity that felt unnatural. Rural observers described the object as a glowing ball crossing the sky from one horizon to the other, changing color from white to red to a blue-white glare as it moved. When it disappeared behind distant hills or forest, there was a pause, a moment of uncanny silence, before the sound arrived, a thunderous volley of crashes and bangs that rattled windows and shook doors in their frames. One composite of many such witnesses might be imagined as a middle-aged settler standing outside his wooden house with a mug of tea in hand. He notices the light first, a growing brilliance to the north that makes him frown and shade his eyes. The sun seems to be in the wrong place. As he watches, the brightness swells and takes shape, revealing a blazing sphere dragging a long, luminous tail. His heartbeat quickens. The chickens in the yard scatter, wings flapping. The dog begins to howl. When the object sinks beyond the tree line, there is a brief, oppressive stillness. Then the shockwave slams into his village. The mug flies from his hand. The sound becomes a wall of noise, a great, tearing crash, followed by a rapid succession of booms that he will later describe to anyone who will listen as like the sky firing guns. Even farther away, up to 400 kilometers from the blast, people saw strange things on the horizon. A sudden pillar of light or fire rising where the forest lay, followed by a dark mushrooming cloud that climbed slowly into the sky. In some places, the ground trembled lightly, making dishes clink and livestock stir uneasily in their pens. In others, The noise came without any visible cause, a low, sustained rumble that people compared to distant thunder that would not end. Across Eurasia, instruments that had never seen Siberia were jolted into response. Seismic stations, some thousands of kilometers away in Europe and Asia, recorded a brief but unmistakable disturbance, equivalent to an earthquake of about magnitude 4.5 to 5 in the region of the blast. Barographs at meteorological observatories traced the passage of atmospheric pressure waves that rippled outward from the explosion, circled the globe, and were detected more than once as they lapped around the planet like the echoes of a cosmic bell. In the hours and days that followed, the sky itself behaved strangely. Over vast portions of Europe and Asia, the night seemed reluctant to fully arrive. Observers in cities thousands of kilometers from Siberia reported unusually bright, silvery night skies. In places as far away as Britain and Northern Europe, people found they could read newspapers at midnight outdoors without artificial light. The effect lasted for several nights, inspiring both wonder and unease. Some thought it a sign of volcanic activity, others a portent of war, while a few scientists quietly noted changes in atmospheric transparency that suggested a high-altitude haze of dust and ice scattering sunlight long after dusk. On the ground in Siberia, the immediate human response unfolded in fragments, scattered across the taiga like the impact's own shockwaves. In one camp, a hunter staggered upright, ears ringing, nose filled with the sharp stink of sap and scorched resin, trying to understand why his familiar hunting ground was now a field of shattered timber. In another, a family crawled from the remains of a collapsed hut, brushing splinters and dust from their hair, blinking at the pale, smoky light. Someone called out a name and got no answer. Someone else shouted a prayer. A child wailed, a thin, high sound that cut through the stunned quiet. The immediate injuries were crude and physical, burns to faces and hands from the flash, blunt trauma from being hurled against walls, trees, and the hard earth, lacerations from shattered planks and flying debris. Some people reported temporary blindness or dazed, tunnel-like vision in the minutes after the flash, as if the world had become a washed-out photograph slowly regaining contrast. For kilometers around, livestock panicked, reindeer bolted from their corrals, dogs howled and snapped at invisible threats, horses trembled and refused to be led. Fear, as always, sought a story. Among Evenki families, the language of spirits and omens surfaced first. Some believed a powerful sky spirit had hurled down fire in anger, or that a great shamanic battle had taken place above the clouds, its echo rippling into the human world. Others, influenced by Orthodox Christianity and the sermons of itinerant priests, whispered that perhaps it was a warning from God, a sign of the approaching end of days. Old legends of fiery serpents and celestial hunters were revived in hastily murmured explanations around campfires that night. Meanwhile, in more distant towns and villages well beyond the flattened forest, people tried to fit the event into their own frames of reference. In some communities, the sequence of dazzling light followed by booming reports and shaking ground felt disturbingly like artillery fire. Russia lived in an age of rising tensions and intermittent conflict. Rumors of new weapons or border clashes were never far from anyone's mind. A few peasants later told interviewers they had been certain, in those first moments, that war had broken out, and they were hearing the opening salvos of some distant, incomprehensible battle. As the day wore on, the physical traces of the blast began to intersect with the slower movements of human curiosity and administration. Messengers and traders traveling through the region brought garbled stories to trading posts and small administrative centers, accounts of forests knocked flat, as if by a giant hand, of a blinding fire in the sky, of a thunderclap that lasted minutes instead of seconds. Some of these tales were dismissed as exaggeration or drunken talk. Others were noted with interest and then buried under more immediate concerns like taxes, harvests, and family disputes. With no photographs, no telegraph wires humming with urgent signals, and no trained observers on the scene, the Tunguska explosion at first remained a local mystery, more rumor than report. Far away from the blast site, however, the instruments of a new scientific age had noticed. At seismic stations scattered across Eurasia, delicate needles traced sudden, sharp motions onto soot-blackened paper drums. At meteorological observatories, barographs recorded peculiar pressure oscillations. The Tunguska blast had launched powerful atmospheric waves that raced outward at the speed of sound, spreading over continents and oceans. At some observing posts, the wave was recorded more than once, as it circled the globe, faded, and then reappeared from the opposite direction like a slowly diminishing echo. Yet the most uncanny sign for ordinary people beyond Siberia came not from needles and paper drums, but from the sky itself. In the nights after June 30, residents of Europe and parts of Asia stepped outside to find that darkness had been diluted into something strange and luminous. Reports from Britain, Scandinavia, and as far south as Central Europe spoke of pearl-colored, shimmering night skies that never seemed to fully go black. Letters to newspapers described people reading outdoors at midnight by a diffuse, silvery light without gas lamps or candles. In some places, photographers managed to take clear pictures late at night without using flash, their plates exposed by a glow that seemed to come from nowhere. Meteorologists and astronomers puzzled over the phenomenon. Some suggested that high-altitude ice crystals or dust were scattering sunlight long after the sun had dropped below the horizon, a kind of accidental mirror thrown up in the upper atmosphere. Others, less cautious, speculated about distant volcanic eruptions or even subtle changes in the sun itself. No one yet knew that, decades later, similar noctilucent clouds and bright night skies would be reproduced when rocket exhaust and spacecraft injected particles into the upper atmosphere, strongly suggesting that the Tunguska blast had likewise lofted material high enough to alter the way the world looked after dark. For people on London streets or in the fields of Sweden and Scotland, however, the luminous nights were less a puzzle than an experience, beautiful, eerie, and a little unsettling. Some took advantage of the conditions to prolong outdoor work or play, marveling at the way familiar landscapes glowed under gentle, ghostly light. Others felt a prickling unease, sensing that something in the natural order had shifted, even if they could not say what. Churchgoers and mystics, farmers and city dwellers alike reached for language of omens and portents, as humans have always done when the sky behaves in ways that defy memory. Back in Siberia, as the first day turned into the first night after the explosion, the survivors within 100 kilometers of ground zero faced a more immediate set of problems. Many had lost shelter and stores of food. Some found their wells fouled with debris or their paths to neighboring camps blocked by logjams of fallen timber. Forest routes that had been known and trusted for generations were now impassable, transformed into tangles of splintered trunks and shattered branches. Under the dim light of the extended northern twilight, small groups began to move cautiously through the debris, calling for missing relatives, salvaging what they could from destroyed storage huts, and trying to assess the new shape of the world around them. A sense of profound vulnerability settled over many, a realization that, whatever the cause of the blast, it had come from above, from a realm beyond their control or even understanding. Elsewhere, in offices and observatories far from the taiga, the data from that day began to coalesce into a set of anomalies in need of explanation. Seismic traces with no earthquake, pressure waves with no storm, bright nights with no nearby volcano. For the moment, these remained scattered curiosities, clipped and filed, discussed in small circles of specialists, and then set aside. No one yet grasped that these disparate clues, flattened forests, frightened witnesses, glowing skis, and twitching needles were all facets of a single event. The taiga, vast and sparsely inhabited, kept its secret. The flattened trees radiating from an unseen center lay unvisited by any scientist for almost 2 decades, slowly weathering under snow and sun. The people who had lived through the blast told their stories around fires, in trading posts, and to occasional curious officials, their memories mingling with folklore and local beliefs. The wider world, wrestling with political upheavals, rapid technological change, and its own human-made disasters, allowed the cosmic blow that had struck Siberia to fade into the background noise of history. But the story of that morning was not finished. The flattened forest and the bright nights, the strange readings on distant instruments, and the whispered tales of fire from the sky, all of these waited for the day when someone would travel into the heart of the devastated taiga and begin, at last, to read the landscape as evidence. Only then would the Tunguska event emerge from rumor and curiosity into the realm of scientific mystery, setting the stage for the next chapter in its long, unfolding narrative. To understand why such an enormous event could remain, for a time, little more than rumor, it helps to step back and look at the country it struck. In 1908, the Russian Empire was a giant with unsteady feet. Its territory stretched from the Baltic to the Pacific, a patchwork of old aristocratic estates, peasant villages, burgeoning industrial centers, and vast, little-mapped frontiers like Siberia. It had railways and factories and universities, but also illiteracy, poverty, and unrest simmering just below the surface. Only 3 years earlier, in 1905, the empire had been shaken by revolution and violent crackdowns, and though the immediate crisis had been contained, nothing felt truly settled. The countryside where Tunguska occurred lay far beyond the main arteries of power. Siberia functioned as prison, frontier, and resource storehouse all at once, a place to send exiles, build rail lines, and extract timber and minerals, but not a region anyone in St. Petersburg imagined as central to daily life. The state had only the thinnest presence there, scattered officials, small military detachments, and a few church representatives trying to bind remote communities into the empire's spiritual orbit. Scientific expeditions did sometimes venture into these lands, mapping rivers or cataloging flora and fauna, but such journeys were costly, slow, and hard to justify without an obvious strategic or economic reward. When the First World War erupted in 1914, whatever attention might have turned toward a mysterious Siberian blast was swept away. The empire hurled itself into a conflict it was ill-equipped to fight, straining its railways, factories, and administrative systems to the breaking point. Scientists who might have been free to chase cosmic mysteries found themselves pulled into military work or struggling simply to keep their laboratories functioning amid shortages. Then came 1917, revolution, the collapse of imperial rule, civil war, famine, and chaos. In those years, even the most dedicated natural philosopher had more immediate concerns than a rumor of flattened trees in a distant forest. And yet the story of Tunguska did not entirely vanish. It lived on in fragments, in the memories of Evenki herders and Russian settlers, in scattered regional reports and local chronicles, in curious mentions of a meteorite fall in Siberia, in the faint tracings on archived seismograms and barograph charts. Years later, in a very different Russia, these threads would be picked up by a man whose persistence would drag Tunguska from the realm of legend into scientific history. That man was Leonid Alexeyevich Kulik. By the early 1920s, the empire that had existed in 1908 was gone. In its place stood the Soviet Union, born from revolution and civil war, determined to transform a largely agrarian society into an industrial modern state at speed. For the new leadership, science was not a luxury but a tool, a way to harness natural resources, build infrastructure, and prove that socialism could master nature as effectively as, or better than, any capitalist power. In this atmosphere, opportunities existed for scientists who could frame their work as both intellectually valuable and materially useful. Kulik was one of those scientists. Trained as a mineralogist and geologist, he had an enduring fascination with meteorites, solid fragments of cosmic material that sometimes survived their fiery plunge through the atmosphere to rest in Earth's crust. To him, these were not just curiosities, they were physical pieces of the solar system's history, samples from places humanity could not yet visit. If such objects could be found within Soviet territory, they were both scientific treasure and potential raw material. In 1921, more than a decade after the Tunguska blast, the Soviet Academy of Sciences organized an expedition to survey meteorites that had reportedly fallen within the new state's borders. As Kulik sifted through old reports and regional accounts, the scattered mentions of a colossal explosion over the Podkamenaya Tunguska River began to stand out. There were descriptions of forests knocked flat over vast areas, of fire in the sky, of thunder that went on and on. To Kulik, steeped in meteoritics, These stories did not sound like earthquakes or volcanic eruptions. They sounded like a meteorite fall of extraordinary size. If that were true, then somewhere in the remote taiga there might lie a massive body of meteoritic iron, perhaps tens or hundreds of thousands of tons, waiting to be found. Such a find would be a scientific coup and might also carry economic potential in a resource-hungry Soviet state. With this dual promise in mind, Tunguska transformed in Kulik's imagination from a curiosity into a mission. The first surveys did not bring him to the heart of the mystery. The Siberian wilderness closed ranks against him. Limited funding, poor transport, and the sheer difficulty of traversing rivers, bogs, and insect-choked forests meant that the party could not push all the way into the area of greatest reported devastation. They gathered information instead: eyewitness testimonies, local law, and geographic impressions that strengthened Kulik's conviction that something extraordinary had occurred there. He returned without a crater or a meteoritic mass to show, but with enough detail to argue that a focused expedition aimed specifically at Tunguska was justified. Those testimonies were vivid, and together they began to sketch not just an explosion, but a flight path across the sky. In villages and camps scattered over hundreds of kilometers, people pointed in roughly the same directions when asked where the fiery thing had come from and where it had gone. Many described seeing a bright body appear low in the southeastern or southern part of the sky, then streaking obliquely toward the north or northwest, its path shallow rather than plunging straight down. Others recalled a glowing pipe or elongated object crossing the horizon from east or south of east toward the opposite quarter, trailing a thick, luminous tail. At Vanavara, a remote trading post roughly 70 kilometers south of the eventual epicenter, residents still remembered the morning when the sky seemed to split in two above the forest to the north, and a sheet of fire unfurled across the heavens. Shopkeepers and hunters told Kulik how, in an instant, the daylight flared into something harsher and hotter, and how the walls and windows of their wooden buildings shook as if seized by invisible hands. Men recalled running into the muddy street in their undershirts, convinced the world was ending, while children clung to their mothers and wept. Some said the fireball had first appeared to the southeast as a small, bright star, then swelled and turned bluish-white as it swept northward and dipped behind the trees, followed by a blast so powerful it knocked them from their feet. Farther away, in a town like Kyansk, more than 100 kilometers from the blast, the stories took on a different texture, less immediate terror, more bewildered confusion. Villagers there spoke of a long, luminous sheaf of fire or fiery broom crossing the sky along the northern horizon, descending at an angle from east to west or from southeast toward northwest. They described how the object's head seemed small compared with the blazing tail that filled much of the sky, and how its color shifted from orange or red near the first sighting to an almost unbearable white glare before it vanished. When it disappeared beyond distant hills, there was a strange pause, and then rumbles like distant artillery began to arrive in separated volleys, 10 or more sharp booms over the span of a quarter of an hour, that made windows rattle and set crockery dancing on shelves. In Evenki camps along rivers and game trails, elders told Kulik of yurts whose roofs had been torn away by the blast wind, of whole families knocked unconscious by the shock and lying dazed for hours amid torn canvas and shattered poles. Hunters described being out on the land that morning and first noticing a peculiar, growing brightness to the southeast, low above the treetops. As they watched, a brilliant ball of fire or a glowing log swept overhead, moving toward the northwest, so bright it cast clear, moving shadows of trees on the ground. Some said that after it passed, they could still see a faint, shimmering band hanging in the air along its path, like a ghostly trail, before it twisted and thinned into something like a ragged, high cloud. Again and again, as Kulik listened, certain images repeated: a sudden blinding fire in the sky, unbearable heat, a wall of sound and wind, the forest laid low as if mowed. Peasants and nomads, orthodox villagers and animist herders alike reached for the same metaphors. Many described the event as like artillery, the sky itself firing salvos that shook the earth. Others spoke in the language of faith, light as punishment, divine warning, or a trial sent from above. For most of them, there was no word like asteroid or comet ready at hand. What they had was their own experience and the stories that helped frame it. Kulik, trained to think in terms of angles and directions, began turning these stories into lines on a map. Each witness's pointing arm, each remembered from there to their motion, became a rough azimuth, a direction along which the fireball must have been seen to move. When he combined these with the radial pattern of the fallen trees at the blast site, their trunks pointing away from a central zone like compass needles blown outward, he arrived at a picture of an object entering from the east or southeast and traveling toward the west-northwest before it exploded high above the taiga. The details would be debated and refined by later researchers, but even in the 1920s, the broad outline was clear enough. This had not been a straight-down strike, but a glancing blow from space along a shallow path. These trajectory clues deepened rather than diminished the mystery confronting him in what he came to call the telegraph pole forest. Everything pointed to an incoming body moving at tremendous speed along a shallow course, shedding light, heat, and roaring sound as it came. The forest fall showed that an enormous amount of energy had been released at a point high above the ground, centered near where the bare trunks now stood. And yet, at that central point, there was no crater, no splintered mass of stone or iron, no obvious remnant to match the violence of the flight that witnesses had described. Back in the cities, Kulik turned these accounts into leverage. He became a one-man lobbying force, writing reports and speaking to colleagues, learning to phrase Tunguska in terms that would appeal to Soviet planners. This was not just a hunt for an academic footnote. It was a search for cosmic iron, for raw material, and for knowledge that could place Soviet science at the forefront of a new field. He argued that the country that first fully understood such events would be better equipped to protect itself from them, or to exploit the resources they left behind. Convincing the authorities took time. The young Soviet state was beset by reconstruction tasks, rebuilding railways, restoring industry, stabilizing agriculture. Funding expeditions into remote forests to search for a rock that might or might not exist was not an obvious priority, but the new regime also prized bold, demonstrative feats, and Tunguska had the allure of both a riddle and a potential resource. Eventually, Kulik won the support he needed. In early 1927, nearly 19 years after the explosion, he set out again, this time with a clearer mandate and a specific goal: reach the blast site itself. The journey from Leningrad to the central Siberian taiga was an expedition in stages. Trains took the party eastward along the great rail lines, exchanging stations, languages, and climates as they went. At one town, the last real railhead, they transferred to horse-drawn sledges, following frozen rivers and winter tracks. As spring advanced, they shifted again to boats and then to foot, hauling their supplies over thawing ground, through bogs and stands of conifer that seemed to have no end. Once more they passed through places that had felt the blast's edge. At Vanavara, now their last substantial settlement before the Great Emptiness, Kulik took time to interview anyone old enough to remember 1908. He listened to a shopkeeper describe the way the air had suddenly turned hot and the loud crack that sent jars toppling from shelves. He heard from a hunter who, as a boy, had been knocked flat in the yard and had later watched with a child's horror as the adults in his family argued over whether to flee, pray, or simply wait and see if the world ended. Women recalled clutching icons and screaming as they poured out of their houses into a street filled with dust, barking dogs, and the din of shuddering buildings. These memories, now nearly 2 decades old, still carried the rawness of trauma. Beyond Vanavara, there were no more permanent streets or shops, only trails and rivers and the quiet of the taiga. The final legs of the journey were made on foot and with pack animals, trudging through dense undergrowth, fording streams, and climbing low ridges that gave brief, tantalizing views over the endless forest. The men swatted insects, nursed sore feet and shoulders, and pushed on. On an April day in 1927, they crested one such ridge, and the character of the forest abruptly changed. Ahead of them, the ordered verticality of the taiga dissolved into chaos. Instead of upright trunks stretching uniformly toward the sky, they saw a vast expanse where trees lay on their sides, their roots torn from the ground, their crowns all pointing roughly away from a common center. It was as if some colossal hand had pressed down upon the forest and then swept outward, flattening everything in its path. As the expedition moved deeper into this zone, the scale of the devastation became clearer. By rough estimate, the area of leveled forest extended over thousands of square kilometers. Trunks lay in tangled heaps, some scorched, others simply snapped. Underbrush had regrown in the years since, softening some of the edges, but the fundamental pattern persisted, a radial fan of destruction pointing back toward an unseen source. Kulik was elated. Here at last was proof, physical, inescapable, that the event had been real and vast. The flattened trees were like frozen shockwaves in wood, a permanent record of the direction and force of the blast. He and his team began measuring orientations, taking photographs and sketching maps. The radial patterns strongly suggested an explosion above the ground, not a conventional impact gouging a deep crater. But Kulik still believed that a massive meteorite, perhaps broken into fragments, must lie somewhere near the center. As they moved toward what the pattern indicated as ground zero, the forest changed again. Instead of trees lying flat, they encountered a zone where trunks still stood upright, but were stripped of branches, bark blackened or peeled away, silhouettes stark against the sky. The men dubbed it the telegraph pole forest, rows of bare, dead trunks resembling the poles and wires of human communications, but here silent and broken. This inner zone was profoundly unsettling. It did not match the popular image of a meteorite crater, nor did it fit neatly with expectations of how an ordinary forest fire might behave. There was charring, yes, and signs of intense heat, but also patterns of stripping and scorching that hinted at a fierce, downward blast of energy rather than flames creeping along the ground. The absence of an obvious, gaping hole where an enormous rock should have plowed into the earth confronted Kulik with a dilemma. He had found devastation on a scale few had imagined, confirmed eyewitness testimonies, reconstructed a plausible trajectory, and documented a radial pattern of destruction that pointed to a powerful, focused explosion. But there was no crater, no colossal chunk of iron, no smoking mass buried in the soil waiting to be claimed. Instead, there was a strange, branchless forest, a scar in the trees rather than in the ground. Kulik refused to abandon his central hypothesis. Convinced that the meteorite must still be there, he turned his attention to other possible signs, depressions in the ground, odd-shaped bogs, or ponds that might conceal impact pits. In the marshy lowlands south of the main devastation, he noted several roughly circular swamps and bogs that at first glance resembled small craters now filled with water. These, he thought, might be places where fragments had struck and then become submerged. With the limited tools and manpower available, he attempted to investigate one such bog by partially draining it and probing the sediments below. The work was grueling. Mud, water, and decaying vegetation fought every effort to impose order. When his team finally reached the bottom, they did not uncover a meteorite fragment, but the remains of an old tree stump, its roots still set in place. Whatever had created that depression, it was not a recent cosmic impact. Still, the expedition's results were transformative. For the first time, detailed ground observations, photographs, and maps documented the true extent and pattern of the Tunguska devastation. The image of leveled forest in a butterfly-shaped or radial pattern, with a central zone of standing, branchless trunks, entered scientific and popular consciousness. Kulik had turned Tunguska from a tale of fire in the sky into a concrete, measurable phenomenon, a landscape puzzle demanding explanation. In the years that followed, he returned to the region more than once, driven by a mix of curiosity, ambition, and a sense of unfinished business. Each trip brought new hardships, illness, logistical setbacks, equipment failures. Yet he persisted, refining his maps, improving his estimates of the blast area, and collecting soil and peat samples in hopes that microscopic traces might reveal the nature of the visitor from space. Primitive aerial photographs, taken under difficult conditions, captured from above the same radial pattern the team had walked through on foot, adding another layer to the emerging picture. Kulik never did find the massive, metallic body he sought. The absence of a crater and large fragments would become, over time, one of Tunguska's central riddles and a key clue pointing away from a conventional impact and toward the idea of a high-altitude airburst. But in the moment, his work was less about final answers than about defining the problem. By the mid-1930s, thanks largely to his efforts, Tunguska was no longer merely a rumor of distant thunder. It was a documented event with boundaries, a known anomaly etched into the Siberian forest. History, however, was not kind to Kulik. As Europe and Asia slid toward another global conflict, he, like many of his generation, was swept up in events beyond his control. During the Second World War, he served his country and was eventually captured by enemy forces. He died in a prisoner of war camp in 1942, never learning the full story of the object that had exploded over Tunguska decades earlier. Yet his legacy endured in the photographs of toppled trees, in careful notebooks filled with angles and distances, in the soil samples that would later be re-examined with more sophisticated techniques, and in the very idea that a remote patch of taiga could hold answers to questions about how Earth and the cosmos interact. He had carved the outlines of the mystery into the scientific record. Others, in later generations, would fill in the interior. In the years after Kulik's expeditions, the Tunguska forest became more than a geographical oddity. It turned into a kind of open-air laboratory for anyone trying to understand how cosmic objects die in Earth's skis. The leveled trees, the telegraph pole core, the lack of a crater, and the scattered eyewitness accounts formed a puzzle that resisted easy answers. Scientists, often working far from Siberia, tried to fit these clues into the existing framework of impact science, and in the process discovered that the framework itself needed to change. Wikipedia +1. Before Tunguska, most thinking about collisions from space revolved around craters. A large meteoroid or asteroid was imagined as a kind of bullet. It plunged through the atmosphere and slammed into the ground, carving out a hole whose size and shape could be related back to the body's mass, speed, and angle of entry. There were known impact structures on Earth and plenty of craters on the Moon to back up this model. Explosions in the air did occur, of course. Smaller bolides flared across the sky and detonated harmlessly at high altitude, but these were considered the lesser, more theatrical cousins of the true, crater-forming strike. Britannica +1. Tunguska appended that hierarchy. Here was an event that, by all indicators, released energy on the scale of a large nuclear weapon. Modern estimates often fall between about 10 and 20 megatons of TNT equivalent, yet left no obvious pit in the ground. The destruction was real and measurable. Roughly 2,000 square kilometers of taiga flattened or severely damaged, perhaps 80 million trees knocked down or stripped. The shockwave and thermal radiation was strong enough to burn skin and ignite fires dozens of kilometers from the epicenter. And still, the soil at the center held no great mass of alien rock. Whatever had come from space had done its worst without ever touching the. Slowly, the idea of a meteor airburst moved from curiosity to central hypothesis. In this picture, the Tunguska object was a relatively small cosmic body by astronomical standards, tens of meters across, traveling at tens of kilometers per second, which encountered such extreme aerodynamic pressures and heating in the thickening air that it catastrophically disintegrated between roughly 5 and 10 kilometers above the ground. The energy released in that breakup did not radiate uniformly in all directions like an idealized bomb blast. Much of it was focused downward along the incoming trajectory, driving a powerful, downward propagating shockwave that slammed into the forest. This vertical hammer blow could explain why trees directly beneath the explosion were left standing but stripped and burned. The shock came from above, while trees farther out were knocked over radially by the outward-moving blast front. Science Direct +4. Under this framework, the missing crater was no longer a contradiction. It was a signature. The forest became a record not of a rock colliding with the ground, but of a body losing a war with the atmosphere. The air, at those speeds and densities, might as well have been stone. As the airburst idea gained traction, attention turned to a deeper question: what exactly had exploded? Two main contenders emerged. On one side stood the comet hypothesis. Comets are composed largely of ice mixed with dust and embedded rocky material, fragile assemblages sometimes described as dirty snowballs. They are less dense and structurally weaker than solid rock asteroids. A cometary nucleus entering Earth's atmosphere might be expected to disintegrate high up, its icy components vaporizing and dispersing, leaving behind only fine dust. Early on, this seemed to mesh beautifully with Tunguska's key features: tremendous atmospheric explosion, negligible large fragments on the ground, and reports of unusually bright, silvery night skies over Europe and Asia in the days that followed, suggestive of fine material high in the atmosphere scattering sunlight long after dusk. The British meteorologist and astronomer F.J.W. Whipple articulated this idea in 1930, proposing that Tunguska had been caused by the atmospheric breakup of a small comet, APS +2. On the other side was the stony asteroid hypothesis. This view held that the Tunguska body was more akin to an ordinary rocky meteoroid, denser and stronger than a cometary nucleus, but still vulnerable to atmospheric stresses at hypersonic speeds. In the 1980s, Czech-American astronomer Zdeněk Sekanina delivered a particularly influential critique of the comet picture. He argued that a typical icy comet approaching along the reconstructed shallow trajectory should have begun to disintegrate much higher in the atmosphere, at altitudes where the air is thin and pressures are low. The Tunguska explosion, by contrast, appeared to have occurred deep in the lower atmosphere, where only a comparatively strong, cohesive object could have survived long enough to reach before breaking apart. Ed Sabs, Harvard +1. Sekanina and others noted further that if the Tunguska object had been a large enough icy body to account for the explosion's energy, it would likely have shed enormous amounts of volatiles over a long visible path, possibly leaving more obvious long-term signatures in the upper atmosphere. Instead, the event's atmospheric effects, while dramatic in the short term, faded within days. Over time, additional dynamical studies of possible pre-impact orbits suggested that the object's path was more consistent with an origin in the main asteroid belt than with the elongated, often highly inclined orbits typical of many comets. Science Direct +3. Supporters of a cometary origin did not concede easily. They pointed out that comets are a diverse class. Some are thought to be largely exhausted of near-surface ice, cloaked under refractory dust or rock that could make them behave more like weak asteroids. Others proposed hybrid models in which a stony mantle encased icy interiors, or in which fragmented cometary material might still deliver a concentrated blow under special conditions. The debate sometimes took on a philosophical tone. Tunguska sat at the boundary between categories as much as it did at the edge of the taiga, journals, NAS Publishing +1. Beyond observatories and laboratories, the first analysis of Tunguska came not from scientists, but from editors and reporters trying to make sense of scattered, second-hand reports. In the weeks after June 30, 1908, regional newspapers in Siberia and European Russia began to carry brief, sometimes confused notices of a mysterious explosion in the east. A paper in the Irkutsk region, relaying accounts from peasants in remote districts, described a glowing, bluish-white body that moved for minutes across the sky before vanishing behind the forest, followed by terrifying thunder and trembling ground. Another local sheet summarized witness talk of a huge sheaf of fire falling behind the woods, of houses shaking, and of villagers convinced that a planet had fallen. These early articles were short on explanation, but rich in imagery, preserving in print the metaphors that ordinary people reached for when their world briefly stopped behaving as expected. Ica +1. Far to the west, newspapers in Europe confronted a different facet of the event, the uncanny glow of the night sky. In London, Paris, and cities across Britain and the continent, correspondents filed stories about luminous nights and self-lighted streets in the first days of July. Editors marveled that people could stroll outdoors at midnight reading their papers without lamps, and some ran anecdotal pieces describing late-night games or impromptu gatherings held under the pearly shimmer. Observers noted peculiar silvery clouds and long-lived streaks that glowed well past twilight. Public speculation ranged from distant volcanic eruptions to changes in the sun, and a few religious columnists treated the glow as a potential sign of approaching upheaval. No one, at that stage, connected these ethereal nights with a blast in a remote Siberian forest, RMG +2. Russian papers, closer to the source, but constrained by distance and priorities, offered a mix of curiosity and resignation. Some provincial journals printed short reports about an explosion in the taiga or meteorite fall north of Irkutsk, often tucked between notices of crop conditions and official decrees. They relayed how windows shattered in villages hundreds of kilometers from the epicenter, how people fell to their knees in fear, and how herders spoke of fire in the sky. A few editorials hinted at frustration that no immediate official inquiry had been launched, but the empire was already grappling with its own internal crises, and the incident had occurred in what one article bluntly called a desolate and uninhabited region. With no known towns destroyed and no confirmed large death toll, the state saw little reason to dispatch costly expeditions into the wilderness. Apps +2. These early press reactions, fragmentary and often speculative, nonetheless played a quiet role in shaping the trajectory of later research. Years afterward, when Kulik and others went hunting for eyewitnesses, they combed old newspaper files as carefully as they did Pete Boggs, using the brief, breathless notices as guides to which villages had seen what and when. The headlines about blue-white fireballs, falling planets, and nights turned to day became, in retrospect, the first public record of an event that would only gradually be recognized as one of the most significant natural explosions in modern history. Psi+2. As the classification debate played out, another thread of research focused less on labels and more on mechanics. Exactly how does a body like the Tunguska object fail in the atmosphere? Modern high-fidelity simulations treat an incoming meteoroid not as a rigid bullet, but as a complex, possibly fractured aggregate that experiences crushing pressures, intense heating, and evolving internal stresses as it barrels through thickening air. Portions may begin to crack or shed mass at very high altitudes, creating a trail of smaller fragments that continue inward. When a critical combination of pressure and internal weakness is reached, the body undergoes a runaway fragmentation, an explosive disassembly rather than a tidy, single break, NTRS, NASA +1. These processes were dramatically illustrated by Chelyabinsk. Detailed reconstructions of that event showed how the stony body began to fail in stages, with multiple fragmentation episodes culminating in a main airburst that generated the strongest shockwave at the ground. High-speed video and satellite data captured flares and brightening events along the trajectory, each corresponding to abrupt increases in energy deposition as new surfaces were exposed. By comparing these real-world signatures with hydrodynamic models, researchers could calibrate their understanding of how material strength, internal flaws, and entry angle control, where and how an object disintegrates. Wikipedia +2. When this Chelyabinsk calibrated modeling was applied back to Tunguska, it helped resolve some long-standing ambiguities. If one inputs a stony asteroid of roughly 50–80 meters, with plausible internal structure and strength, entering at a moderate angle and speed similar to that inferred from eyewitness trajectories, the simulations naturally produce a major airburst at heights of around 8–12 kilometers. The downward-focused shockwave and thermal pulse at those altitudes are sufficient to flatten trees over an area on the order of a couple of thousand square kilometers, generate the observed overpressures at large distances, and inject material into the stratosphere capable of producing bright nights without leaving a surface crater. MaxMag +2. In this way, Tunguska and Chelyabinsk became bookends in a developing science of atmospheric impacts. Tunguska was the enigmatic, historical case, poorly instrumented but massively energetic. Chelyabinsk was the smaller, thoroughly documented modern analog. Together, they anchored models that now inform how space agencies and hazard analysts think about the spectrum of near-Earth object threats. NASA +1. One key lesson that emerged is that size is not destiny in a simple way. Objects tens of meters across are too small to cause global climatic catastrophes of the kind associated with dinosaur-killing, multi-kilometer impacts. But they are large enough, if they explode at the wrong height over a city, to cause devastation comparable to a large nuclear detonation, without any of the geopolitical warning that accompanies human-made weapons. A Chelyabinsk-scale object over an urban center can shatter windows, collapse vulnerable structures, and injure thousands. A Tunguska-scale object could level an entire metropolitan region, National Academies +1. Another sobering realization is that such objects are hard to spot. Surveys over the past few decades have made major progress in cataloging near-Earth asteroids larger than about 1 kilometer, dramatically reducing the risk of a surprise global-scale impact from that size range. But smaller bodies in the tens to hundreds of meters remain far less completely tracked. Many are simply too dim to detect with current ground-based surveys until they pass close by, or, as with Chelyabinsk, enter the atmosphere. Statistical studies suggest that Tunguska-class impacts are rare on human timescales, perhaps occurring every few centuries to a few millennia, whereas Chelyabinsk-class events may recur every few decades to a century, Britannica +1. From a planetary defense perspective, this shapes priorities in complex ways. On the one hand, the largest objects, those capable of global or hemispheric catastrophe, remain the top targets for discovery and long-term tracking. Their potential consequences are so severe that they warrant special attention. On the other hand, the events Earth is most likely to experience in the coming centuries are not dinosaur killers, but Tunguska or Chelyabinsk-type airbursts, regional disasters that could kill millions if they occurred over a densely populated area. Small enough to be stealthy, large enough to be deadly, they occupy a difficult middle ground, Science Direct +2. As modeling improved, policy slowly followed. In the 2010s and 2020s, agencies like NASA, ESA, and various national and international bodies began to formalize planetary defense programs. NASA established its Planetary Defense Coordination Office to oversee detection and response efforts, and missions such as DART, the Double Asteroid Redirection Test, were conceived and launched to demonstrate that humanity could, in principle, alter the trajectory of a hazardous asteroid by kinetic impact. Although DART targeted a much larger object than Tunguska's progenitor, the underlying message was broader. Impacts are not purely acts of fate. With enough warning and the right technology, they can be managed or even prevented. National Academies +1. Even more speculative concepts, using powerful lasers to push threatening objects, fragmenting them with interceptors, or deploying swarms of smaller spacecraft to alter their orbits, are being actively studied. Some proposals focus explicitly on the challenge of short-warning, small-body threats, systems that could, in principle, intercept a Chelyabinsk-like incoming asteroid minutes or hours before impact and break it up into less dangerous fragments, trading one larger airburst for many smaller, higher-altitude ones, News, UX +1. In all of these discussions, Tunguska looms in the background as both a warning and a touchstone. It is the archetype of a large, destructive airburst in recorded history. Whenever scientists or policymakers ask, what would happen if an object like this arrived over a city? They turn, implicitly or explicitly, to Tunguska's flattened forest, its estimated energy release, and the patterns of environmental damage Kulik first measured. When risk analysts estimate how often nature might deliver such an event, they calibrate their models in part by saying, we know at least once, in 1908, it happened here. Origins, OSU +1. There is an irony in this. A remote, sparsely populated corner of Siberia, the sort of place empires often overlook, ended up providing the data that shape how a technologically advanced civilization thinks about one of its most fundamental existential risks. The Evenki herders who watched the sky burn and felt the ground heave beneath them could not have imagined satellite telescopes or kinetic impact missions. But the shock they experienced, the trees that fell around them, and the stories they told afterward became part of a chain of understanding that now extends from the taiga to space agencies and observatories around the world. For the scientific community, Tunguska's legacy is thus twofold. It is a case study in the physics of airbursts, how objects break, how energy couples to the atmosphere and the ground, how shockwaves and thermal pulses carve their signatures into forests and instruments. And it is a reminder of the deep connection between local events and global questions. A blast over a lonely river valley in 1908 forced scientists to rethink how space and atmosphere interact, pushed them to refine models of small-body impacts, and, a century later, helped motivate the creation of institutions and missions dedicated to ensuring that when the cosmos next throws something similar in Earth's path, humanity is not caught entirely unaware. On the morning of February 15, 2013, more than a century after the sky burned over Tunguska, another cosmic visitor arrived over Russia. This time, the target was not a remote river basin, but the vicinity of a modern industrial city, Chelyabinsk, in the southern Urals. People were driving to work, children were sitting in classrooms, office workers were settling behind their desks. Dashcams were running, smartphones were in pockets, and the sky at first glance looked utterly ordinary. Wikipedia +1. Shortly after 9:20 a.m. local time, a brilliant point of light appeared high in the sky, moving rapidly from the southeast toward the northwest. Within seconds, it had become a blazing fireball, brighter than the sun, its white-hot trails stretching across the blue. Shadows snapped into stark relief on the snowy streets, and drivers instinctively reached for sun visors or glanced upward in disbelief, their cameras inadvertently recording what would become some of the most studied few seconds of atmospheric entry in history. YouTube Wikipedia. The object, an asteroid roughly 18-20 meters across, entered Earth's atmosphere at about 19 kilometers per second. As with Tunguska, the increasing pressure and heat of the air overwhelmed its structural strength, and it began to fragment high above the ground. The main airburst occurred at an altitude of roughly 30 kilometers, releasing energy equivalent to about 400-500 kilotons of TNT, some 20-30 times the yield of the Hiroshima bomb, but still only a fraction of Tunguska's estimated power. The light from the fireball was intense enough to cause temporary flash blindness and eye pain in people who stared directly at it. Science +2. The shockwave reached the ground a little more than a minute after the flash. When it arrived, it did so as an invisible wall of pressure that swept across Chelyabinsk and surrounding towns. Windows shattered in an irregular oval tens of kilometers wide, shopfront glass exploded inward, ceiling tiles dropped, and doors slammed. Around 1,500 people required medical attention. Studies suggest even more were injured, but never formally counted. Almost all of them hurt not by falling rocks from the sky, but by shards of flying glass and fragments of damaged structures. Dozens suffered eye injuries, concussions, or ear damage from the sudden overpressure. Science Direct +2. For scientists, Chelyabinsk was Tunguska in miniature, but this time the instruments were ready. Infrasound stations around the world recorded the low-frequency boom of the airburst. Weather and Earth-observing satellites captured the bright trail and subsequent dust plume from above. High-speed dashcam videos provided time-stamped visual records from multiple viewpoints. Within days, triangulation and orbit reconstruction efforts had produced a detailed picture of the meteor's path. A shallow entry from the direction of the sun, one reason it had gone undetected by existing telescopic surveys, and a breakup sequence that matched, in exquisite detail, the kind of fragmentation models originally developed in part to explain Tunguska, PMC, NCBI, NLM, Ni+3. Unlike Tunguska, Chelyabinsk left behind tangible, recoverable pieces. Almost immediately after the explosion, residents began finding small, blackened stones punched into the snow, fragments of the shattered asteroid that had cooled and fallen out of the disintegrating fireball. In the weeks that followed, organized search parties and local volunteers scoured the countryside, ultimately recovering thousands of individual pieces ranging from milligram-sized grains to stones weighing several kilograms. The largest single mass, about 650 kilograms, was later retrieved from the bottom of Lake Chebarkul after divers and engineers cut through thick ice and mud to reach it, collecting meteorites +6. Laboratory analysis revealed that the Chelyabinsk meteorite is an ordinary chondrite of type LL5, a stony meteorite with relatively low total iron content, but containing about 10% metallic iron alongside silicate minerals such as olivine and low calcium pyroxene. Thin section studies, X-ray diffraction, and geochemical measurements showed that the rock is a breccia made of several lithologies: lighter colored chondritic material, darker shock blackened material, and veins of fine-grained impact melt. Microscopic inspection revealed networks of fractures and veins filled with once molten metal and sulfides, evidence that the asteroid's parent body had experienced at least one major collision in deep time that heated, compressed, and cracked it long before it ever reached Earth. New Scientist +5. Isotopic and argon dating studies suggested a complex thermal history, with an intense impact event roughly 1.7 billion years ago and a younger disturbance around 30 million years ago, both recorded in the meteorite's minerals. The shock features, melt veins, high-pressure mineral phases, and pervasive fracturing had an important consequence for atmospheric entry. They made the asteroid mechanically weaker, more prone to fragmenting under dynamic pressure. In a sense, the violent past recorded in the Chelyabinsk stones may have helped protect modern Earth by ensuring that the body broke apart high in the atmosphere rather than reaching the ground as a larger, intact mass capable of carving a crater and causing far worse local damage. Online library, Wiley +2. These forensic details fed directly back into models of the airburst. By knowing Chelyabinsk's bulk density, composition, and internal structure, researchers could constrain the material strength parameters used in hydrocodes that simulate entry and breakup. When those tuned models were applied to Tunguska, they supported the idea that a somewhat larger stony asteroid with comparable composition and similar pre-existing weaknesses could have penetrated to lower altitudes before undergoing a runaway fragmentation, producing an airburst powerful enough to flatten millions of trees, yet still leaving only microscopic traces of extraterrestrial matter in the soil and peat. Meteorites +5. Indeed, investigators at Tunguska have long reported such microscopic traces, tiny magnetic spherules rich in iron and nickel, and subtle anomalies in platinum group and other elements in peat layers corresponding to 1908. These particles, millimeters to microns in size, are exactly the sort of residue one would expect from a stony body that vaporized and condensed in the atmosphere rather than striking the ground in one piece. Taken together with Chelyabinsk's macroscopic meteorites, they help bridge the gap between a thoroughly documented modern airburst and the more elusive, century-old catastrophe in the Siberian taiga, pollen flora +2. In this way, Chelyabinsk acted as a Rosetta Stone for airburst physics and meteoritics. It translated the abstract language of equations and computer code into direct, observable consequences: broken windows, injured people, damaged buildings, recovered stones with shock veins, and melt pockets. When those same tools and insights were then pointed back toward the Tunguska forest, the picture that emerged was strikingly consistent. A larger, structurally weakened stony asteroid, tens of meters across, entering along a shallow path and failing in the lower atmosphere in a catastrophic airburst that dwarfed the power of 2013 but followed the same essential script, NTRS, NASA +2. If Chelyabinsk refined the physics of Tunguska, it also sharpened its message. The 2013 object approached Earth from near the direction of the Sun, a blind spot for many ground-based telescopes that scan the night sky. It was not discovered in advance. There was no warning, no countdown, no public alert. Only after it exploded and its shockwaves swept across Chelyabinsk did global networks light up with news and video. In that gap, in the hour before the boom, when the asteroid silently fell toward an unsuspecting city, lay one of the most troubling truths Tunguska and Chelyabinsk together reveal. Even in an age of satellites and surveys, some cosmic threats can still arrive unannounced. NASA +2. In the years following Chelyabinsk, planetary defense efforts accelerated. Agencies that had long argued for systematic searches for near-Earth objects found a more receptive audience among policymakers and the public. The event became a staple of presentations at scientific conferences and United Nations meetings on space hazards, often shown side by side with historical reconstructions of Tunguska to illustrate a spectrum, from the largely unobserved wilderness blast of 1908 to the thoroughly recorded urban-adjacent airburst of 2013, Space +2. In 2016, the United Nations General Assembly formalized what advocates had already begun to practice. It proclaimed June 30, Tunguska's anniversary, as International Asteroid Day, a yearly occasion to raise public awareness about asteroid impact hazards and the steps being taken to mitigate them. Space agencies, observatories, and educational organizations now mark the date with talks, simulations, and outreach events, explicitly linking the distant roar over the Siberian taiga to contemporary efforts to map and monitor near-Earth space, UNUSA +3. At the same time, the focus of technical work shifted from pure detection to demonstration. If a hazardous asteroid were discovered on a collision course with Earth, could anything be done to avert disaster? On September 26, 2022, humanity moved from theory to experiment with NASA's Double Asteroid Redirection Test, DART. The spacecraft, a compact, uncrewed probe, deliberately slammed into Dimorphos, the small moon of the asteroid Didymos, at a speed of about 6.6 kilometers per second. From Earth, telescopes watched the brightness of the system and precisely measured the orbital period of Dimorphos before and after impact. The result was unambiguous. The impact shortened Dimorphos's orbital period by 32 minutes, the first time humans had measurably altered the motion of a celestial body. Wikipedia +2. DART was aimed at an object that posed no threat to Earth, but its success carried clear implications for real hazards. It showed that a kinetic impactor, a high-speed spacecraft used as a projectile, can, in principle, nudge an asteroid's orbit by a controllable amount. For large bodies discovered years or decades before a potential impact, such small changes could add up to a complete miss. For smaller, Tunguska-scale objects discovered too late for subtle deflection, the problem is harder, but the physics illuminated by DART, Chelyabinsk, and Tunguska together inform more aggressive concepts, interceptors that could fragment or disrupt an incoming body to ensure that any resulting airbursts occur higher and less destructively, or last-minute missions that trade elegance for brute force mitigation. National Academies +2. The broader planetary defense architecture now being assembled, survey telescopes on the ground and in space, coordinated international response plans, deflection technology demonstrations, can be read as a slow, methodical answer to the question Tunguska first posed in 1908. Then, the Earth was struck without warning, and the only records were flattened pines and frightened stories. Today, the goal is to ensure that the next Tunguska-class visitor is discovered early, tracked precisely, and, if necessary, gently redirected long before its path intersects a city or a forest. International Asteroid Day, with its talks and panels and public-facing campaigns, is the cultural counterpart to those technical efforts. A reminder that the cosmos is not a static backdrop, but a dynamic environment through which Earth moves, sometimes sharing space with rocks and ice that do not care where they fall. Asteroid A+2. Chelyabinsk also changed how risk was perceived outside the scientific community. For many people, Tunguska had always occupied a hazy space between history and legend, a curious anecdote about a forest flattened once, long ago. But smartphone footage of a blazing fireball streaking over modern city, followed by a shockwave that sent glass raining down on office workers and schoolchildren, made the abstract suddenly intimate. News broadcasts replayed the clips for days. Social media carried them around the world within hours. When scientists described the event as a wake-up call, the phrase stuck, because it matched what many viewers felt. If this could happen on a random winter morning in Russia, it could, in principle, happen anywhere. The conversation +2. In the policy world, Chelyabinsk added urgency to discussions that had begun in the shadow of Tunguska. The United Nations had already endorsed the creation of two key international coordination mechanisms: the International Asteroid Warning Network, IAWN, a consortium of observatories and agencies that share data on near-Earth objects and potential impact scenarios, and the Space Missions Planning Advisory Group, SMPAG, a forum where national space agencies can coordinate possible deflection or mitigation missions. After 2013, these frameworks began to move from paper to practice, with regular meetings, shared simulations, and tabletop exercises designed to explore how the world might respond if a real impact threat were identified. NASA +1. Within NASA, the Planetary Defense Coordination Office, PDCO, took the lessons of Chelyabinsk to heart. Its mandate now explicitly includes not only the detection and tracking of potentially hazardous objects, but also the development of impact scenarios and communication protocols with civil protection agencies such as FEMA. In joint exercises, scientists, emergency managers, and policymakers walk through hypothetical impacts. A Tunguska-scale object discovered years in advance, a Chelyabinsk-scale body detected days ahead, or a surprise airburst discovered only after satellites see the flash. Each drill forces participants to confront uncomfortable questions about evacuation, public messaging, misinformation, and international coordination under time pressure. National Academies +1. All of these efforts share a common, unglamorous first requirement: find the rocks. Early detection is the single most important factor in turning an impact from an unavoidable disaster into a manageable problem. The sooner an object is discovered and its orbit refined, the more options exist, ranging from doing nothing if it will miss, to targeted evacuations if it is too small for deflection but headed for a populated area, to full-scale deflection missions if the body is large and the warning time is measured in years or decades. Science Direct +1. Ground-based surveys such as Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona have already discovered tens of thousands of near-Earth asteroids, dramatically shrinking the pool of kilometer-scale objects that could threaten civilization. But they remain less efficient at finding smaller, darker bodies in the tens to hundreds of meters, range exactly the size class implicated in Tunguska and Chelyabinsk. These objects can be faint, appear close to the sun in the sky, or approach from directions that current telescopes monitor only intermittently. Filling that gap is a central goal of upcoming survey missions, Astronomy +1. Foremost among these is NASA's NEO Surveyor, a dedicated infrared space telescope designed specifically to hunt near-Earth asteroids from a vantage point near the Earth, Sun L1 Lagrange point. Unlike optical telescopes, which see reflected sunlight, an infrared observatory can detect the heat emitted by asteroids, making it less sensitive to an object's surface brightness or color. This allows NEO Surveyor to spot both dark and bright bodies more uniformly and to search regions of sky closer to the sun that are difficult from the ground. If launched on its current schedule in the late 2020s, it is expected to find the vast majority of near-Earth asteroids larger than 140 meters within about a decade, and will significantly improve discovery rates for smaller bodies as well. The Space Review +3. On the ground, the Vera C. Rubin Observatory in Chile, an 8.4-meter telescope built for wide, repeated imaging of the entire visible sky, will contribute in a different way. Its high-cadence, all-sky movie will not only discover new asteroids, but also repeatedly measure their brightness variations, helping to determine spin rates, shapes, and binary companions. That information feeds back into deflection planning. A loosely bound, rubble pile asteroid may respond very differently to a kinetic impact than a monolithic rock, and a binary system like Dimorphos requires particular care in choosing where and how to strike. Astronomy +1. Together, NEO Surveyor, Rubin, and their international counterparts form the observational side of the answer Tunguska demands. They are the eyes that, in principle, can ensure that no object the size of the 1908 impactor arrives entirely unannounced again. But eyes alone are not enough. The rest of the system, impact risk models, communication protocols, decision-making frameworks, and in the extreme case, deflection technologies, must also be in place and tested before they are needed. Science Direct +1. International Asteroid Day sits at the cultural and political interface of these technical efforts. Each June 30, institutions from space agencies to universities to amateur astronomy clubs host lectures, live streams, and public observing nights, using the Tunguska anniversary as a narrative hook to explain what near-Earth objects are, how they are detected, and what might be done if one were ever found on a collision course with Earth. Campaigns such as the 100X Declaration, launched by Asteroid Day's founders, have called for dramatically increasing the rate at which potentially hazardous asteroids are discovered, arguing that knowledge is the cheapest form of planetary insurance humanity can buy. Wikipedia +3. These outreach efforts matter because planetary defense ultimately depends on sustained political and financial support. Building survey telescopes, flying deflection missions, and running international exercises all cost money and must compete with many other priorities. Tunguska alone, distant and half-mythical, might not have been enough to anchor that case in the public mind. Chelyabinsk, with its broken windows and viral videos, provided the vivid modern companion that made the older story feel real again. Together, they form a narrative that can be told in classrooms and legislative hearings alike. This has happened, we have seen it, we understand the physics, we know at least in outline what to do, space +2. For all the numbers and models, the true measure of these events is written in human lives. In Chelyabinsk, the shockwave did not just shatter glass, it disrupted a city's rhythm. Office buildings were evacuated in confusion, phone networks were briefly overwhelmed, and more than 1,000 people spent part of their day in clinics and hospital corridors having cuts cleaned and bandaged, eyes examined, eardrums checked. Schools cancelled classes en masse, not because buildings had collapsed, but because their windows were gone and winter air poured into classrooms where children had been reciting lessons only minutes before. Parents hurried through streets littered with broken glass to collect their children, alternating between relief and anger that they had been so suddenly and so unexpectedly put in danger. Meeting organizer, Copernicus +2. In the days after the airburst, the work of recovery was surprisingly prosaic. Plywood and plastic sheeting over broken panes, emergency crews checking damaged roofs and facades, municipal workers sweeping up glass from sidewalks and playgrounds. Local glaziers and construction firms found themselves inundated. One Chelyabinsk window repair company reportedly ran advertisements that bluntly asked, "Have your windows been shattered by the meteorite?" A darkly humorous reminder of how quickly disaster becomes business for some. Residents shared stories online of fear and near misses, but also of small kindnesses. Neighbors helping elderly people tape up windows, strangers offering rides when public transport was disrupted, teachers calmly shepherding terrified children out of damaged schools. Planetary +2. Psychologically, the event left an imprint that is harder to catalogue than broken glass. Many people spoke of a lingering unease when they looked at the sky or flinched at sudden loud noises, their bodies remembering the jolt of the shockwave. Others described a paradoxical sense of gratitude, echoing one Russian expert's remark that the meteor had been a blessing in disguise, a warning shot that injured but did not kill, and that might, in the long run, help prevent something worse. Chelyabinsk's residents, like the Evenki before them, folded the event into local identity. For years afterward, small fragments of the meteorite were sold and traded as souvenirs, tokens of the morning when the universe quite literally dropped in. Wikipedia +5. For the Evenki and Russian settlers near Tunguska in 1908, recovery was less coordinated, more a matter of endurance than organized response. There were no emergency services to replace lost herds or rebuild crushed cabins. Families whose reindeer had been killed by the blast or whose hunting grounds lay in the heart of the flattened forest had to adapt on their own, shifting camps, seeking new pastures, or relying more heavily on trapping and fishing until herds and game recovered. In some accounts, communities temporarily abandoned certain areas not only because of practical damage, but also because they considered them spiritually tainted by the fire from the sky, preferring to leave those places to the spirits that had, in their view, so violently manifested. Ica +2. Over time, the physical landscape healed faster than the social and cultural fabric. Trees regrew, rivers kept flowing, and animal populations slowly returned. But the stories of the blast, told and retold around fires, and later to visiting researchers, became part of how local people understood both the capriciousness of nature and the distant power of the state that had largely ignored their disaster. In later decades, Evenki communities would face new forms of disruption from logging, fires, and proposed hydroelectric dams along the Tunguska and neighboring rivers, so that the 1908 event came to be remembered alongside a longer history of sudden, often unwanted changes imposed from outside, whether by cosmic visitors or human projects. Cambridge +4. Yet in both Tunguska and Chelyabinsk, the aftermath is also a story of resilience. People rebuilt homes, replaced windows, returned to classrooms and camps, and found ways to weave extraordinary events into ordinary life. The Evenki resumed herding and hunting. Chelyabinsk's residents went back to offices and factories whose facades now bore new double-glazed panes. Meteorites were picked up, studied, and in some cases, set on shelves as conversation pieces. Scientists arrived, took measurements, and left, but the people who lived under those skis stayed, adapting to landscapes that now carried an extra layer of meaning. Online library, Wiley +2. In the taiga north of the Podkamenaya Tunguska River, the forest has grown back. New generations of larch and pine rise where their predecessors were flattened, their roots entwined with the weathered remains of trunks that still, in places, lie like fallen matchsticks beneath the moss. The scars are no longer obvious to a casual eye. Animals cross the blast zone without noticing, snow falls and melts, seasons turn. But in core samples taken from the peat, in the alignment of buried logs, and in the faint anomalies of trace elements, the memory of that morning endures. Tunguska, TSC+1. Likewise, in museums and laboratories around the world, small pieces of Chelyabinsk rest in glass cases and sample trays. Polished slices reveal chondrules and melt veins. Thin sections under microscopes show shock features that speak of ancient collisions and a fiery end. School groups peer at them. Researchers grind tiny chips to powder to analyze isotopes and minerals. Each fragment is a physical footnote to the Tunguska story, a reminder that what flattened the forest in 1908 and what rattled windows in 2013 are not abstractions, but real stones that once drifted silently through space. Physics.A, 8+2. From a certain angle, the whole arc can be seen as a dialogue between Earth and the sky. In 1908, the sky spoke first, in a language of light and shockwaves, and humanity struggled for decades to understand what had been said. Now, in the early 21st century, Earth has begun to answer back, not with words, but with telescopes, simulations, and a small spacecraft hurled deliberately into an asteroid's path. In that exchange lies a new kind of relationship between a planet and its environment, not passive victimhood, but cautious, evolving stewardship. NASA +2. Seen from this angle, Tunguska, Chelyabinsk, and Dart form a kind of three-act story. In the first act, the universe announces its power with a blast over an empty wilderness, leaving behind a riddle that a determined mineralogist and his successors spend a century attempting to solve. In the second, the same sort of event plays out over a modern city under the gaze of cameras and sensors, turning abstract risk into broken glass and injured neighbors, and scattering stones that laboratories can dissect grain by grain. In the third, a small spacecraft slams into a harmless asteroid moon, and in doing so, proves that knowledge gained from those earlier acts can be turned into action. The story is not finished. There will be more objects, more close passes, more debates over how much to invest and how soon. But thanks in large part to a summer morning in 1908 and a winter morning in 2013, the question is no longer whether such events can happen. It is how prepared humanity chooses to be when they do.